All right, so now lastly we need a dynamic equation. We need to understand the dynamics of the shutter closing. So when we have a dynamic equation, we want to start the shutter at maybe 150 degrees and then let it go and let it snap closed. So there's going to be a force on this thing and it's going to snap closed. So for a dynamic equation for something rotating about a point, so if we have this shutter and we're going to have a force by the spring, and then we have this longer lever L, the shorter lever M, and we have this big mass, this thing is going to swing closed, and we need this to swing closed. In a rotating system, you typically have inertia times theta double dot, where this is angular acceleration. It's like radians per second squared. Then that equals a torque, tau, which is my torque. So let's look at this a little bit. The inertia is this lumped mass out at distance L. So from physics class, you knew that the inertia is just mL squared. Torque is this radius times this force. So the torque in physics class was R cross F, but we're going to make everything at right angles for ease of assumption. So it's just this distance R times this force F. Now that force F is a function of theta. So my force is a function of theta. It's not a constant. It actually is proportional to where the angle of the shutter. So now when I write out my dynamics equation, I have the inertia times theta double dot equals the torque, which is R times the force, which is a function of theta. And we know what the function of theta, the force is a function of theta. We just calculated that in the last video. So we have something that looks like something times theta double dot equals something times theta is what we're going to have. Because the force of theta from the last equation looked like minus kr theta plus some gigantic c. So we're going to have an equation that looks like ml squared theta double dot equals minus k r theta, but I've got to multiply that by an r, so minus kr squared theta plus this rc. And then I gave you that the mass, I just took the shutter and weighed it. I got the mass to be 0.174 grams. I got L to be 19 millimeters, R to be 3.5 millimeters, and we're going to make a delta T to be 0.005 seconds. So now you can lump this equation. My dynamics equation is going to look something like theta double dot equals the force proportional to theta times r divided by ml squared. So theta double dot, my acceleration, looks like minus kr squared theta plus kr squared pi plus kr times 8.636 times 10 to the minus third plus br, that whole thing divided by ml squared. So if you know the position, you substitute in all the values and you know the angular acceleration at one instant in time. Then we have to keep repeating this. Again, if we know the position, we calculate a theta double dot. So that's going to be an equation. Then the next equation says, what is velocity? So my velocity today equals the theta double dot that I just calculated in step 1 times a delta t plus theta dot of yesterday. How did I get that? Well, you don't have to derive it, but it's really a definition of a derivative. The definition of a derivative says theta double dot is equal to theta dot today minus theta dot yesterday divided by delta t. And I just brought the delta t up here and did some algebra. But this is the second equation you have. You can calculate the velocity that the shutter is moving at based on the acceleration, based on a delta t, and based on its previous velocity. So the previous velocity plus the acceleration times a delta t gives me my new velocity. Then if I look at my third equation, I'll tell you that my third equation says the angular position today, so this is position, equals a half of my velocity of today, which is calculated in step 2, plus my velocity of yesterday times a delta t plus my position of yesterday. So the today's position is 1/2, it's an average of my velocities times the delta t plus whatever my yesterday's position is. And then what you're going to do is loop this many, many times. You're going to loop these three equations many, many times until you simulate the system going from 150 degrees to 180 degrees. So you're going to start off with the system at 150 degrees, but put it into radians, please. You're going to calculate a theta double dot. The theta double dot times some small delta t. You're going to add in the previous velocity. The system starts off with 0 velocity because you start the camera off at 150 degrees, 0 velocity, and then let it go. Then you're going to calculate the new velocity. Then you're going to take the average of the velocities, because this is an average, times a delta t plus my old position. My old position started off at 150 degrees. And then I'm going to calculate my new position, and my new position might be 153 degrees. And then I'm going to loop back, put in 153 degrees, and loop through this. And you're going to do this in Excel because Excel is perfect at going through these equations step by step by step by step.